Thank you, John. Yes, good morning, everybody, or good afternoon, whenever you're listening online or listening back. Thank you for joining this first webinar series hosted by the Maritime Navigation Group. We are first of all looking at autonomous vessels. So this is part one of a three-part series. In this session, we're going to be looking at a high-level overview of autonomous maritime autonomous systems, including some definitions and some comparisons and some current examples. And we encourage you to tune in to our part 2 and part 3, which will be held in 2024. In the second session, we're going to be doing much more of a deep dive into the technical aspects of precision navigation timing challenges and communications challenges for autonomous vessels, and some more human factors associated with those sensors. And then in the third series, the last part of our autonomous vessel series, we're going to be looking more at the regulations, the increasing complexity of navigating in confined waters, and looking at all the challenges around vessel encounters. Then we include autonomous vessels into the mix. So do bear those in mind for the future. I'm now going to hand over to Tom, who's our main speaker for today. Tom Howe has a significant maritime career, both a master mariner, former Royal Naval specialist navigator, a trained accident investigator, and he is a fellow of the Royal Institute of Navigation, being a committee member of our Maritime Navigation Group. Tom, thank you very much for speaking to us today. I'll hand over to you.
Thanks, Donna. So, I've been working closely around the regulatory development of the framework to certify defence shipping in the United Kingdom for the last 8 years or so. And that's given me some insight into the development of marine autonomy in both defence and the commercial sector. As Ivana says, this Royal Institute of Navigation webinar will provide a curtain raiser for a series of presentations looking at the fascinating world of marine autonomy. In terms of the structure of this presentation, so how we're going to run through the material, the introduction we're firmly into. After that, we'll look at the what. So what are marine autonomous systems and what does the landscape they operate in look like? The what's new, so what's different about marine autonomy? The how, what are the biggest challenges which need to be overcome and how are they likely to be overcome? And then going into the Q&A that John's already spoken about. And I would encourage you to ask any questions as we go along, and we'll address them at the end. Next slide, please, John. So let's take a look at marine autonomy. There's been a lot of press coverage of marine autonomy and a lot of noise as players within the sector project their visions of the future. As ship designers and an independent marine consultancy, we at BMT need to understand autonomy, and that is to say really understand where the technology is now and where it could be. During this webinar, I want to give you an introductory overview to the sector, explain marine autonomous systems, or MAS as they're often termed, and outline some of the challenges and what the future may look like. Next slide, please, John. Let's just say that there's a sizable UK maritime industry. Now, the figures you're seeing on these slides are taken from the DFT. The MAS industry sits within the broader global and UK maritime industries, and it's worth starting by looking at the size of that industry, so the MAS industry, or the overall maritime. Before COVID-19, around 95% of goods imported and exported in the UK were moved by sea, and a strong maritime industry is a strategic asset to the UK. Although there is a general sea blindness among the general public, the fact is that almost everything they use which has been imported arrived by sea. The sector employed 220,000 people in 2019 and was worth 17 billion gross value add to the UK economy. The structure of the maritime sector, with low margins and long asset life cycles, which is a way of saying ships last a long time, means that the sector could be slow to adopt new technologies, with potentially significant gains for countries or organisations able to identify and implement transformational technologies quickly and first. The global autonomous ship market size was estimated to be valued at around 88 billion in 2020, and is projected to reach $150 billion by 2030. MAS could be considered a subsector within the wider maritime technology sector. And as we will see, the autonomous ship is in fact an assembly of technologies. The global wider ship technology market is estimated to grow by over 170% to $278 billion by 2030. And the Government Office of Science predicts that the global ocean economy, as defined by the OECD, including all maritime fishing, offshore oil and gas, will double to $3 trillion by 2030. Although at present the UK market for MAS is small, it's expected to grow as shipping technologies develop both within the UK and abroad, and will have a huge impact on the shipping industry, as in many other sectors. Now let's look at some of the things you may have seen. The examples on this slide, as John runs through them, show that some organisations are investing heavily and clearly identified that autonomy is a source of opportunity. These examples show that the technology is moving at a fast pace and that companies are proactively taking action now to try and maximise their ability to operate in a future autonomy market. As with any fast-moving environment, or as the UK government have coined it, industrial revolution, technology develops rapidly. There are many challenges, but autonomy, or a ramping up of automation, is far from new in other domains, and there are significant economic opportunities in marine autonomy. Next slide, please, John. So having introduced this and set the scene, let's look at the what of marine autonomy. Next slide, please, John. So what is marine autonomy? What are MAS? Next slide, please. Not exactly this, no. At one end of a large spectrum, this would of course be an autonomous ship, so something without crew being driven around by artificial intelligence and machine learning. But marine autonomy is far more nuanced and complex than this. Critically, we must recognise that autonomy is not bound by AI and machine learning. Marine autonomy is fundamentally the expansion of the role of technology in seaborne platforms into tasks traditionally performed by humans, with the ultimate headmark for some in the industry of a self-driving ship. Next slide, please. I'm not going to go into any detail about AI in the scope of this presentation, but it's worth quickly looking at where it fits into autonomy, as the terms are often conflated in general discourse. As we see, autonomy refers to a system's ability to operate without human intervention on a continuum, with higher levels indicating greater control by the system and lower levels involving more human intervention or control. Autonomy in a complex application, such as a ship, is clearly not a simple 1 or a 0. It's likely to be a gradient of system control. So what about artificial intelligence? AI is a field of science that aims to create machines or software that can perform tasks that normally require human intelligence, such as reasoning, learning, and problem solving. AI can also help us process large amounts of data and make decisions based on patterns and insights we find. AI is a broad term that covers many different technologies, such as machine learning, natural language processing, computer vision, or robotics. We can regard AI as a set of tools which can be applied to some of the problems which must be overcome in order to make a complex system of systems function autonomously. But it is just that, set of tools. There are specific challenges in the assurance of AI, which would more than fill another presentation. Within the scope of this one, we'll stop at this point and consider AI as a tool in a toolbox. So back to autonomy. The next slide, please, John. The International Maritime Organization, the IMO, defines full autonomy to be where the operating system of the ship is able to make decisions and determine actions by itself. This they categorise as a degree or level 4 autonomy, with a further 3 paraphrased as follows. Degree 1 concerns conventional ships with some onboard automation. Degree 2 covers ships that are conventionally crewed but can be remotely controlled. And Degree 3 are ships which are both remotely controlled and uncrewed. In practice, autonomy at Degree 4 can vary according to the scope of the system under consideration, the range of tasks or operations in mind, and perhaps most importantly, the nature of human monitoring and intervention, both in situ and otherwise. Depending upon system architecture or concept of operation, a vessel may transition between degrees of autonomy during the same operation or voyage. The approaches taken by classification societies also merit a mention. Lloyd's Register, Bureau Veritas, and DNV each approach autonomy differently. After initially developing autonomy levels, LR now use accessibility levels of 0 to 5. BV aligns more closely with the IMO's master terminology using degrees alpha 0 to alpha 4, while DNV opts for brief phrases that outline operational decision-making and executional aspects relating to control. I'm not going to look at these approaches in detail. The takeaway here is that each organisation has sought to make the understanding of MAS more accessible by creating boxes. In each case, the extent of human involvement is the defining measure. Recognising that the evolution of autonomy is about the extent and nature of human involvement, Let's look across to other sectors and identify lessons. Next slide, please, John. The first thing to recognise about autonomy is that it isn't new. And the second is that rather than being a binary condition, autonomy is more usefully considered as a gradient. 95% of delivering autonomous platforms in terms of technical requirements lie in core design and engineering applied to a new problem. So things you already know how to do, used in a different context. Finally, the progression through increasingly higher integrations of automation, moving towards fully autonomous capability, profoundly impacts design. The gradient of autonomy is an evolution, not a revolution. And we can see this if we look across domains to commercial aviation. I'm going to apologise to the air navigators watching this for grossly oversimplifying the development of their branch in the past 70 years. If we look at our passenger aircraft of the 1950s, there are 4 crew members required, delivering discrete functions to achieve a commercial flight. The 747 in the 1970s had trimmed that down to 3 by automating some of those functions. By the 1980s, the cargo carrying variant of the 747 could achieve the same function using 2 pilots. The commercial airliner today has 2 pilots, but they could be considered to be system supervisors with reversionary operator roles. The safety increases over that period have been marked, and in some part delivered by removing the human as the instigator in the accident chain. So where is marine autonomy on that gradient today? Next slide, please, John. So marine autonomy, as we look at it today, could be thought of as sitting in the period following the Big Bang of innovation. This is certainly true when we use AI as an enabling tool. It is a rapidly evolving landscape. Critically, it's evolving without a developed international regulatory structure, with levels of regulatory oversight which vary greatly between nations. There are a range of players from small startups to well-funded drivers driven by multi-million-pound investments. When we look closely at the technologies and use cases, we can see a lot of solutions, so technologies people have developed, trying to find problems they can be applied to. Success for marine autonomy means identifying the areas where autonomy is the solution to an existing problem and a genuine value-adding development. So let's look at some areas where autonomy could be part of the solution. Next slide, please, John. So where can autonomy win? What are the areas where autonomy is actually likely to prove to be the solution finding an appropriate problem? 3 obvious use cases are the delivery of military effects, improvements in maritime safety, and a contribution towards the decarbonisation of the maritime. Let's look at each of these in a little more detail. There are more, but it's worth just singling out 3, otherwise we will rapidly run out of time. So looking at the delivery of military effect. I don't want to go into too much detail on military use cases. Suffice to say that they're compelling, but not without their own challenges. It's widely recognised that there is a specific military penalty for failing to achieve autonomy in a timely fashion. And that's framed many of the approaches to autonomy in the military. In summary, we see themes emerging in the application of autonomy in the military, and the things it's going to be good at. Removing people from danger. We already see this in UK mine hunting capability, where uncrewed systems are able to clear minefields, supervised by humans outside the area of danger. Automation clearly has the potential to reduce crew numbers, and crewing is an issue for navies worldwide, as the retention of personnel becomes more and more challenging, as social pressures drive people away from maritime. It has the potential to increase the speed of decision making. It allows us to understand complex situations. It enables the automation against fast threats. It's able to give us persistence in duration, so assets that are able to remain in the battle space for a long period of time. It will allow us to achieve distributed mass, in that small autonomous systems can be produced at scale and cheaply, whereas battleships now cost more than £1 billion. Designing without the need to support people. So reducing or removing hotel services, survivability, or escape and evacuation as design drivers. And that change in design drive is one of the critical aspects of mass, which has the potential to really deliver leaps forward in capability. There are many more, but let's now look at potential environmental impacts of autonomy. So, a recent United Nations report issued further warnings regarding climate change following the 4th IMO greenhouse gas study, which projected a 90 to 130% increase in greenhouse gas emissions from shipping by 2050, based on a business as usual scenario. This prediction contrasts sharply with the IMO's target to halve maritime emissions by the same year. Against this background, the Maritime has much to do to mitigate environmental impacts, and autonomous technology has been offered up by its advocates as having a significant role to play in driving reduction. Many developers have pointed towards the potential for autonomous and automated navigation to benefit the environment by increasing voyage efficiency, thereby contributing to decarbonisation. Autonomy, done well, can improve productivity and fuel efficiency by continuously reacting to small changes with small actions, rather than intermittently responding to larger changes with more significant actions, as humans tend to do. This results in reduced emissions per cargo volume ton transported. Wärtsilä, in a recently published paper titled "The Future of Smart Autonomy is Here," suggested that autonomous solutions can yield fuel savings of 10% or more on longer voyages by optimising vessel routing and speed. Meanwhile, on a 2-hour voyage, a mere 60-second reduction in docking time can cut fuel consumption by 2 or 3%. Autonomy solutions may also maximise fuel efficiency by enabling just-in-time shipping operations, allowing vessels to running ahead of schedule to decrease their speed on approach to ports and minimise loitering time. The Global Industry Alliance to Support Low Carbon Shipping has suggested that a reduction in speed of as little as 10% can lead to a 30% decrease in carbon dioxide emissions. Proponents of technology-enhanced or smart port operations point to autonomous bulk cranes, which reduce vessel turnaround time through optimised load handling, contributing to sustainable port operations. The world's first autonomous and zero-emissions container ship, the Yara Birkeland, transports fertiliser from the Norwegian city of Porsgrunn to deep-sea ports in the towns of Larvik and Breivik. It features automated mooring, autonomous loading and unloading, and sensor integration technology. This dramatically lowers emissions by eliminating up to 40,000 lorry journeys annually in a densely populated part of Norway. One area in which early adoption of MAS has been well funded is the marine survey industry. A number of credible survey companies have achieved 95% reductions in carbon by using remotely controlled vessels to conduct surveys. There are major players in this industry, building 78 and 86 metre vessels designed to be very lean crewed, with many of the previously embarked roles now conducted from remote control centres. This sort of model sees remote control centres spread across the world, for example, Singapore, UK and the US West Coast, operating 8-hour day shifts. This model allows for 35 operators to be taken off the vessel with a demonstrable carbon reduction, and by making the roles in effect day jobs in shore locations, the nature of the workforce becomes far more diverse. Seafarers who can now do the school run every morning and be home for bedtime every night. None of these developments are, in or of themselves, golden bullets, but the mitigation of maritime environmental impact is a game of often fine percentages in which autonomous technologies will play a part. So autonomous technology gains in capability, and the acceptance that the ship design changes we hinted at in the maritime sphere can significantly improve the design of commercial shipping, allowing reduction in drag and increases in efficiency, point to merit in the adoption of autonomy. So there are clear environmental use cases where autonomy will deliver dividends, but what about safety? Next slide, please, John. The safety argument for autonomy is interesting, and we'll look at the navigation aspects of this shortly. Clearly, the removal of crew from vessels removes people from the dangerous environment of the sea, and that offers a clear win for autonomy. Advocates of autonomous technologies also point to the safety dividend delivered by removing the human from the decision-making cycle. And in a world in which the majority of accident investigations ultimately point towards the operator, this is theoretically undeniable. The UK DFT have recognised that new shipping technology could increase safety, health and security standards. The MCA, through the MAIB, have recognised that a consistently occurring factor throughout almost all accidents, incidents and errors is the human element. Between 2011 and 2018, 65.8% of EU member state flagged shipping accidents were attributed to human action, with shipboard operation being the main contributor. In 2022, 1,263 accidents involving 1,351 ships were reported in UK ships or in UK coastal waters. Seafarers spent between 4 and 6 months at sea. on average, leaving their family and friends unsure why they work 10 or 12 hours days. MASS could reduce the need for humans to do dangerous jobs, reduce the risk of human error and the negative social impact of shipping by reducing the number of personnel at sea. However, autonomous technologies as the maker of mariner-like decision-making are immature. We will return to this aspect of it as it's of particular interest in the context of navigation. With any immature technology, a development curve will exist, and initially the mariner-like decision-making of autonomy presents regulators with a safety problem. Over time, it should be anticipated that the consistency and quality of autonomous decision-making will develop to a point where an overall safety improvement is delivered. You'll hear people say it will be a lot easier when all ships are autonomous, but bear in mind that people like to drive boats, and that activity predominantly occurs around harbours. So a fully autonomous sea space is unlikely to evolve. Across the three areas we've discussed so far, military effect, decarbonisation and safety, some of the arguments or projected benefits feel slightly hypothetical as we sit here today, with only limited examples in actual operation. In reality, we are in the foothills of autonomy. Next slide, please. Previously, we said that 95% of what was needed to make marine autonomy true is conventional engineering applied in a different context. So what is new? What sits in the 5%? Next slide, please, John. From the position of a Royal Institute of Navigation presentation, the good news is that the really interesting bit of what needs to be true to make marine autonomy happen lies in the other 5%, and that is mariner-like decision-making. We can split the navigation of a ship into two fundamental processes, as the mod do when looking at the safety of navigation in military shipping. Getting from IMO Mode 3, remote control, to IMO Mode 4, full autonomy, involves the system making mariner-like decisions, and that's what's different about autonomy. So let's look at POAP and COS-P. Next slide, please, John. Basically, POAP and COS-P are the vessel's navigation capability. Provision of the anti-collision plot, or POAP, is basically understanding and applying the coal regs, so not colliding with another ship. Control of safe passage, or COS-P, refers to the PNT, so the position, navigation and timing function, so not colliding with a charted object. Let's take a look at POAP. Next slide, please, John. POAP has been the child star in the spotlight of the discussions which have developed around autonomous navigation. This is probably because it throws up the easiest and most obviously contentious problems. This is a shiny thing and all mariners are magpies. Now, before everyone shuffles towards the edges of their seats and looks forward to a roller coaster of contention, I'm going to say this: POAP is not PNT. So while it resides within the bailiwick of navigation in the nautical meaning, it perhaps fits less so with navigation as understood by the RIN. For this reason, I'm going to introduce the issues and then move on. First of all, POAP can be bound by and understood entirely within the context of the international regulations for preventing collision at sea, known as the coal regs. Next slide, please, John. I'm going to have to talk about the coal regs briefly, and then we'll move through it because it is one of the larger problems. It should be emphasised that the coal regs are statutes and not guidance. This is important because while many old mariners will say no one follows them anyway, and this is true that the standard of application by mariners is variable, this has yet to form the basis of a successful defence following a collision. There's been a lot of debate within the world of autonomy about the application of the coal regs to autonomous vessels. So given that not everyone watching this is likely to be an expert, what do the coal regs do? Next slide, please, John. Basically, they tell mariners how to act when encountering another vessel in a manner which engenders the risk of collision. Where the conduct of mariners falls short in this respect and a collision occurs, they become the basis for determining who was at fault and apportioning blame. One of the issues which has hampered the development of autonomous coal reg software is that the coal regs are published in a small blue book. Next slide, please, John. This is the small blue book. Don't panic, we're not going any deeper than this, the book will stay shut. The small blue book contains the elements of the broader duty for the observance of good seamanship, which constitute the legal obligation between vessels, to which 175 members of the IMO could agree the wording. Part B is the bit which predominantly tells vessels how to act, and like a distant sheep, it is small and woolly. The actual interpretation of the broader duty, and therefore of the words within the small blue book, lie in the underpinning case law, and their appropriate application may not be properly understood at a level which enables the development of good software without significant underpinning of that knowledge of that case law. The COL regs are complex and interlinking in their application, so one rule may rarely be considered in isolation, and furthermore, they're predominantly written in terms which reflect a human operator. The smallness of the blue book and the fact that it doesn't tell the reader any of this useful background context has led to anyone who's passed all the road tests and stood a bridge watch, and many who haven't, believing that they are experts in the COL regs. Next slide, please, John. Many of you will be familiar with this, and I debated whether to include it as it is perhaps unkind, but the point is probably too significant to pass over. It's worth saying that we are all on this curve in everything we try and do that's new. And I'm never showing it to Nigel, my plumber. Unfamiliarity. I prefer the term unfamiliarity to incompetence, as Dunning and Kruger used, as in many cases the developers of marine autonomy have been software developers looking to apply their solution to a maritime problem, rather than mariners with an adequate knowledge of the understanding of the complexity of the COL regs. They were operating in a world of unknown unknowns. This has undoubtedly led to some wasted effort in the earlier days of development, and to many in the autonomy industry calling for changes to be made to the COL regs, often from positions atop the initial summit on the graph. Interestingly, after years of this sort of thing, the IMO stated at MSC 107 that changes to the COL regs for autonomy were not required, and I agree with this position. The COL regs are in large part goal-based, so their interpretations applied to autonomous vessels becomes an issue for regulators in terms of certification, and will over time pass into case law as incidents are arbitrated. To assist the industry, the UK MOD have produced a guide to the COL regs for developers of autonomous systems, which seeks to correct some of the more common misconceptions and explain some of the underlying constraints and principles. Next slide, please, John. Having looked at the COL regs as a challenge on the path to full autonomy, the next one which jumps out is delivering adequate situational awareness. Bearing in mind that the draft IMO MAS code has indicated that a MAS broadly of ship size must always have a human mariner able to intervene if required. Now, there's a lot more detail than that, but in big picture terms, that's the theme which we would expect to see continuing through. And this is a requirement which is likely to feature in the autonomous landscape as MAS grow in size. This fairly simple statement actually leads to a situation in which every MAS will require a remote control centre, or ROC. So adequate situational awareness must be delivered both to the autonomy stack making decisions on board the vessel and to the human overseeing it in the ROC. All of the aspects contributing to POAC combine to deliver a safety critical function. And regulation, properly underpinned by recognised acceptable means of compliance, has not yet been developed. One industry assessment concluded that the COL reg software element alone was a problem requiring an investment of around £10 million and could take up to a decade to mature. Now let's look at control of safe passage. Next slide, please, John. COSP has been the Attic child in the discussions which have developed around autonomous navigation, because it throws up problems which are complex and require an element of understanding before one can engage in the discussion. This is very much a function of the success of GNSS as the invisible utility and a misunderstanding of its vulnerabilities. The ubiquitous nature and high accuracy of GNSS has led to a near universal adoption as the primary and often the only form of position source in autonomous vessels. Systems in which GNSS compasses are proposed as a backup to a GNSS position receiver are unfortunately not apocryphal. It's worth reflecting for a moment on this point, not upon what it says about navigation, but upon what it tells us about the sheer complexity of achieving a fully autonomous ocean-going ship. Our area of interest as navigators is so interesting and diverse, and no one could have attended a RIN conference without coming away dazzled by the breadth and depth of our area, or impressed by the abilities of those pursuing its leading edge. Yet when we raise our eyes and look beyond our own sphere, it becomes readily apparent that the navigation challenge has not been recognised in a safety critical application by those pursuing technological advance. That doesn't tell us that the developers of autonomous systems are naive or foolish, and that's certainly not true. But it does speak to the diversity of deep technical expertise and the plethora of individual system advances within what must be viewed as a complex system of systems, which are required to make autonomous ship operation a certifiably safe reality. For a RIN webinar, this would naturally be the jumping off point for a deep dive into the fascinating challenges inherent in autonomous or automated GNSS independent ocean-going navigation and potential solutions. But I'll rein everything back in and remind myself that this is the introduction. I will, however, point to a couple of significant factors. Next slide, please, John.
In conventional shipping, the absence of reliable GNSS, for whatever reason, has become a challenge. Indeed, a Swedish ferry with 75 passengers on board ran aground only last month, causing a significant oil spill, with the master reportedly fined by the Swedish authorities for reliance on a faulty GPS set. This is avoidable in coastal waters, but when we look into the deeper ocean, in the absence of space-based satellite positioning, one is generally reliant on conventional astronavigation or bathymetric navigation, neither of which have been fully automated to the level which would allow immediate integration into an autonomous vessel, and both of which have significant dependencies, cloud cover and bathymetric survey data being two which immediately spring to mind.
And when we look at bathymetric data, all of the geospatial data which supports operations across the maritime comes into focus. At present, this is produced to be read by a human operator, and the developments required to support machine readability are yet another rabbit hole leading to a different deep specialist wonderland. And within all of these different considerations lies the chicken and egg problem. What is an acceptably safe solution? Given how immature the development of the solution to the autonomous COS-P problem is, how can a regulator possibly be expected to provide a prescriptive, accepted means of compliance? Those are certainly someone else's sandwiches, and I'll leave it floating for a further delve into regulation later in this series. Next slide, please, John. So within the general development of full autonomy, PIAF and COS-P are probably where the biggest blockers to marine autonomy lie, because they're where the third-party risk becomes manifest. Getting the crew off a ship is often a driver in the military effect impact area, but it's not so obvious in the commercial sector, where cheap labour is measured against an expensive capital outlay. It does, however, have big potential for carbon footprint reduction and, in time, safety improvements. The liveliest discussions around the autonomy sector, unsurprisingly given the things we've already discussed, take place around the regulatory aspects of autonomy. The Howe of marine autonomy needs to pass through the coalescing phase after the big bang of innovation before it could emerge as a mature technology. Next slide, please, John. So how do we get to the fully autonomous ship? Next slide, please. The big post-Big Bang coalescing of marine autonomy has to be shaped by regulators. I don't want to go too deeply into this, as I think it forms a presentation in its own right. However, we can't deliver an overview without looking at the regulatory picture. Firstly, looking to the highest international level, regulating mass has implications for safety, legal, and facilitation instruments under the purview of the IMO. An IMO working group was established following a regulatory scoping exercise that was designed to assess existing IMO instruments and see how they might apply to mass and what gaps existed to complete their operation. The scoping exercise was conducted by the Maritime Safety Committee, Legal Committee and Facilitation Committee, examining the relevant treaties under their supervision. The Maritime Safety Committee agreed on a roadmap, developing a goal-based instrument regulating the operation of mass, which as a first step would be in the form of a non-mandatory code for likely adoption in 2025, while a mandatory mass code is to be developed thereafter for entry into force, predicted for 1st of January 2028. The draft of this mass code reveals, as one would expect, a high-level set of directions, the initial implementation of which will fall to individual member nations. For us here in the UK, that means that the Maritime and Coast Guard Agency, the MCA, the commercial mass, and the Defence Maritime Regulator for mod shipping will have to look at that code and decide how to implement it. A lack of certainty in the regulation of mass is potentially impeding investment and innovation. Changes to international law to accommodate mass, agreed through the IMO, are unlikely to be completed before 2028. From an industry perspective, gaps and lack of consistency in the regulatory framework are slowing innovation. Many industry stakeholders are asking for interim regulation and guidance to allow the on-water testing and even commercial operation of mass in UK waters, as well as access to data to support their developments. From a regulator's perspective, HMG's approach to mass was described by the DFT as ad hoc. The MCA are prevented from progressing mass regulation by the existing statute, and are seeking parliamentary time to introduce changes to legislation. The issue is, in summary, that existing UK legislation is premised on ships being manned, setting out roles and responsibilities for people and organisations involved in shipping operations. Commercial ships are regulated through the Merchant Shipping Act, and regulations explicitly or implicitly assume that the ship has a crew on board to operate it, and a pilot, where used, will also be on board. MAST challenges many of these assumptions, meaning that MAST might not, in all respects, be able to comply with the requirements of legislation as written today. To explain what that means, we can look at examples of how MAS under development are operated. Every time a trial of a MAS is organised, the operator must prove the safety case and obtain exemptions from national and international maritime safety requirements for each voyage. This may include load line, safety of life at sea, coal rigs, or safe manning. In addition, trials are often conducted using a manned escort ship, with notices to mariners which warn users of a live MAS trial. Classification societies and insurers also need to make special arrangements to assure themselves that the relevant risks are covered. The larger the MAS and the higher the level of autonomy proposed, the more complex this burden becomes. The more regulations must be accommodated through equivalence and exemption, and this requires the MCA to examine each MAS on a case-by-case basis. This is burdensome. There's been a requirement for the MCA's supporting organisations to develop approaches to assure MAS as well. The regulatory burden has created significant frustrations within the UK MAS industry and has led to some companies moving their operations to other jurisdictions. To their credit, when compared to other nations, the MCA have developed approaches to regulation enabling MAS to progress to the extent possible within the existing law. They've issued Marine Guidance Notice 664, a process for the use of novel technologies, and a new edition of the Workboat Code with an annex covering MAS will be placed before Parliament this month, with an anticipated publication date of the 13th of December. So while it may be burdensome, the structure for the UK does at least exist. In the longer run, this is likely to advantage UK MAS development. Once regulations exist, the complex task of developing proportionate approaches to establishing means of compliance and assurance can mature. I said this is complex, and if we look at MAS as a system of systems, we can start to appreciate the scale of the assurance task. Next slide, please, John. This image does something to convey the complexity for a large ocean-going MAS. Specific areas for consideration include the assurance of the autonomous systems control location, the remote operating centre. The ROC is where the personnel employed to operate or oversee autonomous ships execute that function, and where the port, flag and coastal state obligations, safety, security and environmental considerations and liabilities, in addition to insurance, will likely reside. The ROC as a shore workplace will be governed by different safety regulations to a seagoing bridge. This scaling up of MAS reveals further challenges. How will remote pilotage be exercised, for example? There are so many challenges in here that you could sit here for an entire presentation and just run through issues around the ROC. We then need to consider vulnerabilities in communication, because the ROC has to be able to talk to the MAS. Going back to that requirement for a human master to be able to supervise the ship, you have to have some constant form of communication. This introduces vulnerabilities, communication, data transfer volume, integrity and resilience, all of which require assurance. We need to defend against cyber attack, and this may be more complex than the problem faced by a crewed vessel. Looking to the ship itself, the engineering challenges of uncrewed operation are not to be underestimated. Just think about science fiction films based on the engineer being brought out of suspended animation to unblock a filter, and you can see the marine engineering challenges in an uncrewed ship. There are also ethical considerations which need to be addressed in the development of a fully autonomous ship. When autonomous ships have to decide and all options have bad outcomes, it's important to understand how the system will decide on which option it will choose. None of these are insurmountable, but each challenge requires deep expertise to address. I hope that this quick canter through marine autonomy has been of interest. It is an immense subject, and to try and condense it into a short presentation to lead as an introduction to questions and answers has been a fairly sizable task, but I'd like to leave you with one last set of thoughts. Next slide, please, John. These words of Bill Gates apply to marine autonomy. The progress of marine autonomy will be incremental as we move up that gradient one step at a time. In considering the regulation of mass, it's important not to let the hypothetical issues delay or crowd out immediately technical or regulatory challenges, which need to be addressed to make that next full step. The how of marine autonomy can only be delivered by retaining a ruthless focus on solving the next immediate challenge and not being distracted by the esoteric or the hypothetical. Marine autonomy will move from smoke and mirror press releases and rendered images of futuristic ships into a reality. And in 30 years' time, I can easily see a future where mariner-like decision-making, and in particular navigation, is either executed or supported by autonomous systems with a carriage requirement in all ships, and some ships are fully self-driving. Next slide, please, John. And with that, I'd like to thank you for your attention and hand back over to John.
Well, thank you very much. I learned a lot. So at least for one participant, the effort was well worthwhile. Thank you very much. Fascinating stuff and a great introduction to the series. So we've got one comment online, which is that Cynthia is saying how great it is that this new series is kicked off. So thank you very much for that comment. We've got a couple of questions that have come in advance, which I'm going to ask Ivana to go through. And if anybody would like us to address any questions in addition to the ones Ivana's about to ask, then please pop them in the Q&A now, and we will be happy to do so. So please.
Thank you, John. Thank you very much, Tom. Yes, I've been scribbling away. You've sparked a lot of interest, a lot of ideas in my head. But one thing I want to start with is, can you just tell me what you are most excited about for the future of autonomous shipping?
I think when you look at all the things that autonomy has the potential to deliver, I think the one which will touch most of us most significantly are the safety advances. I think that vision of the future in which autonomous systems are taking the human out of the error chain as instigator in the accident sequence, I think is one of the real things you can be excited about. I'd be quite excited about not being one of the 75 people on the Swedish ferry. And I think that automating that navigation process really will take away some of the things that we see recurring time after time in accident reports. It's a long way off, and there are a lot of things that need to be made true for that to happen. But that's where I think the technology is going.
You talked a lot about economic opportunities, and your autonomy wins. The three were military effect, safety, and decarbonisation. I'm struggling to see. There was a wonderful phrase used in the PNT seminar yesterday about the maritime industry having deep pockets and short arms. How can you see those autonomy wins equating to economic opportunities, knowing that the maritime industry often looks for financial wins, and that some of those safety, decarbonisation aren't necessarily obvious in their financial gains?
So I think, as with all things in the world of autonomy, it's tempting to try and think about the end state. So a world in which a radical and dramatic change has been delivered, and how does that happen? In reality, I think we will see incremental small changes. So phyletic gradualism rather than punctuated equilibrium. And if you look at the potential an autonomous system or a highly automated system has to reduce fuel consumption, that's a money saver. So at the point you could deliver a piece of software to a shipping company, which allows operations to be done more effectively, to a point at which that saves more money than it costs, a step forward in the autonomy journey has taken place. And you then develop the next thing after that. And when you look up 10 years later, a whole load of big changes have happened. But I think it's that model. I think that's when we look at what's happening in reality, it is a series of small technical steps, which as a sum of their parts actually amount to something quite large. But it's going to be in voyage optimization and fuel use optimization. Those are the big ones. When you look further down the line and you actually start to redesign a ship, if you can take that big superstructure off the back, so your human doesn't have to look over the containers, suddenly everything gets a lot more efficient. You can start to change the way you actually design a ship. Particularly And this is where the military use cases are different, because you don't have the same economic drives. Cost is still an issue, but it's not a driving issue. Your ability to fundamentally design a different platform that works in a different way and does something more effectively is in there. You can then carry that over into your commercial ship design. At the moment, all ships look the same, broadly. For a type of ship, it looks like that ship. If you're taking the hotel services out of it, that ship can look different.
Interesting, wonderful. I think we've got some questions online.
Yes, thank you very much for these. You mentioned, so Seamus asked, you mentioned GNSS and positioning, navigation, timing as enablers of autonomous vessels. And what's the role of AIS, automatic identification systems?
So at the moment, AIS presents us with a problem in that the data it's passing is not assured. So if you start reading through the IMO's words on things various, there's a whole set of cautions in there about relying on AIS data. I think if you look, and this is recognised by the IMO, and MSC are looking at how to make changes to AIS to make it more reliable. If you look at the next generation into VDES, so VHF data exchange, we're going to be exchanging larger volumes of data, and there are opportunities in there, in the architecting of that system, to make the data that you're exchanging more reliable. Now, AIS, or the transfer of data about your ship to other ships, is a fundamental thing that has to work for autonomy to work. Now, if you look at, and I said everything about Howe comes back to the Colrex, that's because everything comes back to the Colrex. So the lookout element of your ability of safely navigating your ship requires you to maintain lookout by sight and by hearing. Lots of people in the autonomy sector, bear with me, this is a tangent, but it works. Lots of people in the autonomy sector have said, well, we can't possibly do that, that's ridiculous, you have to change the words. Bearing in mind that the Colrex are goal-based, what that's actually telling you is that you have to have adequate situational awareness, however you derive it. Now, the way we transfer things at the moment is by shapes and lights. So we're using things to convey information visually that a human can pick up. Now, those shapes and lights are telling you things about the condition of your vessel and priorities you may be claiming, information you would wish other mariners to be aware of if you're engaged in a recognised nautical manoeuvre. AIS can do that too. So when you move into VDES, if you deliver VDES in a way that enables you to transfer all of the information that you would be shown by light and shape electronically, the autonomous vessel will have the right level of situational awareness. So it moves AIS from where it was when it was first envisaged in the 90s to a point where it actually becomes something really quite important. So I think it's a fundamental building block in that marine data architecture when you look 20 or 30 years down the line.
Is it true to say that as well as then AIS and satellite navigation capabilities, all autonomous ships have other sensors on board, such as cameras and so on, which are being brought into some situational awareness?
Yes. So you went, because of that remote control requirement and the human oversight part of it, you effectively have to live in two different worlds. So in one of them, you're delivering situational awareness to an autonomy stack, so to a set of ones and zeros algorithms. And the way you do that isn't the way you deliver information to a human. So your ship design data architecture has to be able to deliver situational awareness at an appropriate level to the autonomy stack, however you derive that. But it also needs to be able to deliver human situational awareness to a third-party location. And those two things have to match up. So it's more complex than it looks. And at the moment, we're on that gradient, we're right down at the bottom. So we're driving ships around with people looking through laptop screens. There's a lot that needs to become true before you commit to taking a large, expensive vessel on a transoceanic voyage.
A couple more, and we have a bit of time. So Simon is asking, which regions or countries do you anticipate, or maybe are, the leaders in the development and adoption?
So there are some clear leading nations. Norway are quite a lot, are very forward leaning into this. Singapore, Japan in particular are having a really good look at this. And the way that Japan are approaching this is quite an interesting one, because their drivers are from their workforce. So inside a voyage in Japanese territorial waters, you need a Japanese crew, as I understand it. There aren't that many Japanese people who want to be seafarers, so they're hitting a kind of demographic problem. And they would rather have a Japanese computer driver ship than a Filipino seafarer. You'll see the same thing in America, where the Jones Act prevents you conducting an internal voyage with a foreign crew. So there are places where the way in which they wish to conduct their maritime industry will drive them to a demographic point where high levels of automation become essential. For companies that are driven purely by cost, it's a more difficult argument to articulate, because at the moment, as we said in the presentation, the capital outlays are quite high and the cost of conventional manning are quite low.
The questions are coming in thick and fast now. Okay, for a few more minutes?
Yeah.
Excellent questions as well. So Winston asked, how will product liability issues be resolved or even considered, especially in the case of defective AI?
Let me know when you find out. I mean, good question. No one knows. And there are lots of these, and you would term them hypothetical, but they're not. They are actual real questions that are going to have to be sorted out. The answer to that is we won't know until it actually fails and it goes through legal process.
As a comment from myself, the RIN is also following automated, probably rather than autonomous systems for land-based vehicles. And the whole question about testing, verification, validation is, really quite open at the moment, and a very live debate. So I think that plays into the liability question as well. As
I understand it, in the vehicle market, the manufacturers have said that the liability lies with them. And I think that's an outstanding defensive maneuver if you're the maker of conventional vehicles, because it puts all the liability in the lap of the person building the car that isn't your car. What do you do about a defective AI? I think the answer to that is you've got to head it off at the regulatory phase. So this is a question about, if it's done right, this is a question about assurance rather than a question about how you settle the claim when it goes wrong. It's going to be a separate presentation. It would have to be, because it's a big subject. One of the issues with AI is that it's not explainable. So while it's often right, you can't tell what's going on inside the black box. That doesn't mean it's not usable, it's not assurable, but it means you need to develop approaches for the assurance of AI that adequately mitigate its potential non-repeatability.
Brilliant. In fact, these questions are providing excellent input as well to the second and third in the series, and what I suspect might be about to be a fourth as well. But the next question, we'll take maybe three more. I think we've got time for that. So the IMO degrees of autonomy makes sense. Why do classification societies have different standards or meanings?
It's a good question. So I love it when people say, "Oh, it's a good question." What it means is I'm thinking about it.
That's fair.
The classification societies have got the problem of working out how to assure these technologies slightly before they arrive. And the way we understand things as humans is by putting them in boxes. It's the easiest way to do it. And at the highest level, those IMO boxes make sense. When you get towards the edges of them, it becomes slightly more difficult. And you start thinking, well, I want something slightly different to this. So you see in the defence world levels of control emerging, which are slightly different to the IMO terms. They're all just shorthands for understanding something which exists on a scale in ways which are easily accessible. I think the answer to that is the classification societies are all grappling with their own individual problems. Commercially, the way they work, that will be driven by the people who've actually put something in front of them, because that's the thing they need to work out how to assure. Academics can deal with the stuff that's coming a long way down the line. Regulators have to deal with what's in front of them.
It's a great question and a big topic. Autonomous, automated, driverless, pilotless. And so it goes on. Security of autonomous systems is the next question in a nutshell. How important is it to secure these systems for them to be safely adopted?
It depends what they do. So the answer to that is what's the risk?
Mhm.
It may be that the loss of your system is something that doesn't overly concern you. It may be that that would be a very significant issue. So it will mean different things to different people. And there's nothing different in there. There's, this is in the 95% of, of cyber security that we deal with in every other aspect of modern life. You apply exactly the same approaches to an autonomous ship, and you secure it to the extent you need to for the thing you're using it for.
Mm. And I'm going to try and combine these questions and the last two. Apologies for the folks who asked me if I hash this up, but it's about pleasure and leisure vessels.
Yeah.
And I suspect Rob may be a leisure vessel sailor, as he says. Will all of this bring, it's a part A, will all of this bring some sort of requirement in future on the currently unregulated pleasure vessel sector? And then sort of linked to that is how might ASVs assist in search and rescue? And those are the last two.
Okay, one at a time. So the pleasure vessel is here to stay. People like sailing. That's never going to change. In terms of do you see a regulatory change coming because of this? No, certainly not in the immediate or medium term. No. The way that MAS is being approached by the regulators is that if it can't comply, you can't do it. So it's going to have to fit into the existing framework, and the existing framework is that a yacht doesn't have to have an AIS transponder on it. So your autonomous vessel has to be able to detect the yacht and deal with it appropriately.
Mm-hmm.
There is, if you think about how all of this becomes true, so how does this actually happen? You're probably looking at a short sea shipping MAS vessel that's going from a port to a different port on a route. Mm-hmm. So the operators of those two ports have to think about how to solve their personal problems. So the environment around that port within their categorized waters. You may think that the best approach to this, bearing in mind that the complexity of particularly anti-collision increases dramatically as you enter the port environment and its approaches, that the best way of doing that is to take the situational awareness problem away from the MAS, and as a port authority generate your own service picture that you can assure, and then push that situational awareness to the autonomous vessel, so that it's working off a recognised picture that you both understand. And that's an easy way of making short sea shipping MAS work, because you don't need the difficult parts of situational awareness generation organically within the MAS to be realised before you can start operating it. So the answer to that is you get in your yacht and you sail around as you do normally. There's probably a couple of extra radars and some cameras around the port area that's building a data layer in port operation that you use to understand surface picture and risk.
And
the other one was search and rescue.
ASV's role in search and rescue, question mark?
It's not a use case that anybody's really delved into, because there's not a commercial driver for it at the moment. The things that MAS give you in terms of persistence and distribution are probably useful SAR assets. So I think what they can give you is better vision and wider area coverage than you get with one search and rescue helicopter.
Tom, your job is done. Thank you. Thank you for the questions. And I think I'll hand over to Ivana, if I may, to close this out, please.
Yeah. I love that. I actually really love that last question, because one of my biggest concerns is you take people out of the shipping equation, ocean going, and you've lost your SOLAS requirement for a ship to automatically respond to a distress signal. But if you consider every vessel at sea as a information data gathering device as well, then suddenly you've got a global network of information systems which you could share, which I love the idea of. Anyway,
but
Tom,
the hardest bit in SAR is always finding the guy in the water.
Absolutely, yeah. Right, thank you so much. I'm just going to pick out a few things which I really loved from what you said, and I love the idea of just looking at an autonomous ship as an assembly of technologies. I think that's a really valuable way of looking at it, and looking at autonomous vessels as, to start with, as the expansion of technology into the maritime sector. And you use this lovely phrase, a gradient of system control. And I think that's a really good way of looking at the problem, if you like, and seeing it as a solution and as a tool. We've delved into a lot, which we're going to cover more in future series, and I think you've given us a real taste for. So in part 2, which we're going to look at holding in about February, we're going to look more at the sensor suite on board autonomous vessels. We're going to look at position, navigation and timing, the communications challenges and why we need them. And again, obviously, we're naturally going to touch on regulation, but we're going to try and leave the really big regulation debate to the 3rd series, where we're also going to look at this mixed manning model in different environments, what you do when all the ships come up with the same algorithm of the most efficient route, so you've got more vessels on the same route, and look at managing traffic and all that. So I really encourage you to tell other members, tell other people who might be interested in hearing this again, because this will be available for those who might have missed it, and tuning into the 2nd and 3rd series, where we're going to cover as much as possible about autonomous shipping. Thank you so much, Tom, for the introduction, and John for the technological wizardry
Oh, no problem.
you've accomplished today. And we'll leave it there. Thank you.
Great, thanks everybody.